students, welcome to the next session of Strength of Materials 1. In the previous classes, we have generated shear stress distribution for the various sections. Then we have completed overall shear stress distribution for the section which is a rectangular, circular, symmetrical I section and unsymmetrical I section. Right? Now we are going into one more unsymmetrical section, that is T section. Right? First, what is the thing in T section's shear stress distribution? As it is same, it will be generated or obtained same like I section only. But what is the difference? But in this case, the position of neutral axis is to be defined. Yes, we already know. We have already seen our unsymmetrical I sections. What we have done there? So, for the unsymmetrical I section, firstly we should have to locate the neutral axis. Similarly, T section also, for this unsymmetrical appearing vertically symmetrical. When you see the cross section, it is appearing like a T, and when you see the vertical section, left and right are resembling, but any horizontal axis will not resemble the top and bottom portion. So, vertical symmetry is there, but not the horizontal symmetry. That's why this section is not symmetrical or unsymmetrical. Okay. For such type of unsymmetrical sections, firstly we should have to locate the neutral axis. Generally, for the symmetrical sections, neutral axis will be at geometrical center line, simply at the horizontal, which we draw at half the depth, right? For any symmetrical section, overall depth half, that is our neutral axis line, geometrical center line and centroidal axis line for the rectangle, circular, square and symmetrical I sections. Now, being unsymmetrical, for such type of T's or some unsymmetrical I's, we should have to locate the neutral axis. So, such type of unsymmetrical sections, our first target is generating the neutral axis location. And then what we should have to do is to obtain first, okay, as the section is being not symmetrical. Similarly, as the section is not symmetrical, the corresponding shear stress distribution. Yesterday also we have seen this. So we have observed some shear stress here and somewhere here at the neutral axis some value, and like this some different portions we have got. So there is no symmetry we have observed. When it is a symmetrical I section, the distribution with respect to vertical and down will be same like a mirror image. But the section is not symmetrical, so the shear stress distribution is also not symmetrical. Okay, so that thing only they have given. The shear stress distribution is also not symmetrical. Right? Now I am going into the problem for the T section shear stress distribution diagram. Now, the shear force acting on a section of the beam is 50 kilonewtons. Right. So, the capital F value or the shear force value they have given acting on the section as 50 kilonewtons. Now, the section of the beam is T-shaped and with the dimensions 100 by 100 by 20. Okay. So, we are having the T section with 100 by 100 by 20. As we have already said for the I section also, whatever is the first dimension, that is width of the particular beam. So, width of the particular beam is 100 mm. And the next dimension is the overall depth, whether it is I section or T section, whatever it is, the next thing is the overall depth of the beam section. Okay. For the previous I section, we have observed these two terms, but later they have given two values. This is web thickness, this is flange thickness, like that they have given in statement. But here I am observing 20 mm only. So directly they have given 20 mm. So the same value is the thickness for the flange as well as the web. So for the flange as well as for the web portion, the thickness is 20 mm only. So, this is the way they have given the value. But they have given 100 by 100 by 20. We should have to understand what is 100, what is 100 and what is 20. Okay. So, the section with a width as 100, overall depth as 100 and thickness of web as well as thickness of the flange is 20-20 each. Okay. So, this is our generation of T section. And we have already said what we should have to do for shear stress distribution. We should have to locate the neutral axis. Okay, we will see the remaining problem, then we will go into the answer. And calculate the shear stress at the neutral axis and draw the shear stress distribution diagram for the T section. Okay, we should have to calculate the shear stress at neutral axis level and we should have to generate the shear stress distribution across the depth or over the depth of the beam. Okay. So, as we have already mentioned here, I should have to generate the centroid because neutral axis is always passing through the centroid but may differ from geometrical centerline. Geometrical centerline means total depth by 2. Centroid means so for the area concentrated location. So that area concentrated location and neutral axis will always collinears. Okay. So as I am indicating our T section for generating the centroid. So 100 by 100 20 20 and further use I am calculating the remaining value also which may be useful for me. Which is 80 mm as the height or the depth of the web. Only the web height, web thickness, flange width, flange thickness. Okay, these are the portions. Now I am differentiating this T section into two portions with a small separation. Okay, I am considering that as one part, this one as one part. For these two parts as a unit, it is T. Now I am considering T as one part, flange as web as one part, and for these two portions, I should have to look at the centroidal axis and with the reference from the bottom. Okay, so distance of centroid from the bottom or from the top also you can write, but the corresponding measurement you should have to measure from top level. Okay, now with reference to the bottom axis. Okay, it's just a reference axis. What is the formula for centroid? So I am measuring along y direct. That's why centroidal distance y bar from the bottom is equal to a1 y1 plus a2 y2 divided by a1 plus a2. So a1 y1 plus a2 y2 divided by a1 plus a2. What is this a1? a1 is nothing but 100 into 20 area of the first segment. And next thing I need to do is measurement of y1. What is this y1 measurement? For this area, there is a centroid. For this area, there is a centroid location. Okay. From the centroid location, what is the distance to the bottom axis? That is y1. Okay. So, from the centroid location to the bottom axis, what is the distance? That one is y1. Okay. As I already know, the measurement as 80. So this portion is 80 and plus some portion is there. How much it will be? That is 20 by 2. So which is 10, or if you want you can write as 20 by 2. So A1 y1 and then A2 y2. A2, what is A2? A2 is second segment's area with a width of 20 and a height of 80 into. Again, where the centroid locating for this section? As the section is like this and the centroid may be here. And the corresponding measurement, you can write it as distance of centroid of the second segment from the bottom axis, that is y2, as it is a rectangle and it is connected. So completely from 80 it is at level of 40. So which is 80 by 2. A1 by 1 plus A2 by 2 divided by what I need to do? A1 100 into 20 plus A2 20 into 80. Only thing you should have to remember is taking the top portion separately and bottom portion separately and clubbing again for getting the common centroid of the whole T section. So A1 by 1 plus A2 by 2 by A1 plus A2. In this way we have got the answer as 67.78 and we have got the value, but what we should have to give? We should have to give the position from which reference it is there. Okay, that is 5 kilometers. Okay, from our college, that is 5 kilometers. Like that reference we should have to do. Okay. This reference is given from bottom. Okay. From the bottom axis, the center of gravity is locating, or centroid of the area is locating at 67.78 mm. Similarly, from the top, 100 minus the 67.78 is equal to 32.22. So, centroidal distance from top and bottom is equal to. So, what it is indicating, as we already know, the centroid is the neutral axis. So, hence, the neutral axis is at 32.22 mm from the top and 67.78 mm from the bottom. So, indicating all these things, when we see the picture, it may appear like this. So, what it is showing, see here, we are having the top flange 100, thickness 20, and the vertical member as 80 mm we have said as the web, and the total they have given us 100, and this thickness we have given as 20. And from the bottom, we have generated the centroidal axis line, and that centroidal axis line is at 67.78 from the bottom. As we already know, the centroid line is the neutral axis line. So, this is my neutral axis line. Okay. So, the neutral axis line I have indicated as N at another end, A at another end. So, NA, neutral axis. Okay, X axis, Y axis will write right. So, from the left corner, right corner, like that we will indicate the axis name. So, NA, neutral axis line. And this neutral axis line is at a distance of 32.22 from the top flange, that extreme, and to this extreme. Okay, this is the T-section appearance. Now, what I should have to do, we should have to generate the shear stress distribution for the T-section with respect to this neutral axis. Okay, and also they have given us to calculate the shear stress at the neutral axis level also. While doing the generation of shear stress distribution, we will calculate this as one step. Okay, like we have given for the I section. So, for that, the main formula we should have to remember is tau is equal to FA y bar divided by I into B. So, FA y bar by IB. So, what is this F? Shearing force at the section. A into y bar is area moment above the level and calculating the shear stress. I, moment of inertia of the whole section. B is width of the beam at the level and calculating the shear stress. Okay. So, the common thing is I. So, that I am calculating now. I is moment of inertia of the whole section about the neutral axis. As we have already separated as two segments, here also I am doing as I1 and I2. Okay. So, the separation when you observe, it may appear like this is the first portion and this vertical member is the second portion. So, individual moment of inertia for the first and the second we should have to calculate. Okay, I am calculating that only. I1 is equal to, when you see the neutral axis line is like this and the top flange is like this. Because I am calculating moment of inertia about first part only. Okay, only that part only I am writing. And this dimension is 100. And this dimension is 20 mm. Okay, so 120. And also from the top to the neutral axis, we already know the value, that is 32.22. Okay, now the thing is I, moment of inertia of this segment I should have to calculate. As if it is passing through the centroid, 100, D cube by 12 plus 100 into 20 into what is the distance from the centroid to the axis, that is my y, which is equal to 32.22 minus 10, because it is 32.22 and the leftover portion is half the 20, that is 10. So 32.22 minus 10, which is 22.22 whole square, BD cube by 12 plus AY square. Once summing up, we have got the answer as 105.412 into 10 power 4 mm power 4. Only for the top flange separately. Now I am going for the web portion. So what about this web portion? Again, draw the condition. I am having the web like this. Yes, with the height as 80 mm. Okay. Now we are having the neutral axis at some level which is not at half the distance. See here, that is at 67.78 mm. Okay. We should have to remember that is somewhat upper than the half, because at half means 40 level, right? Okay. So this is 67.78. This is the only second segment, and for this neutral axis I should have to calculate the moment of inertia about the neutral axis level. If this is a common member, 20 thickness and 80 height. So B 20 into 80 cube divided by 12 plus 20 into 80 into. Now what is the y? Y means distance from the axis to the centroid of the section. Okay, distance from the reference axis about which I am calculating the moment of inertia. About neutral axis I am calculating the moment of inertia. So from the neutral axis to the centroid of the section which I am taking now. So this section is having a centroid like this. So that centroid distance is 40 from top and 40 from bottom. Okay, so this is the centroid location. Now what is the perpendicular distance between these two? Centroid of the section, neutral axis of this overall section, and the distance between these two is 67.78 minus 40. So BD cube at 12 plus A into Y square. We have got the second segment's moment of inertia as this is Ry, because that is the neutral axis distance and the centroid distance of the section. Okay, CG of the section. Once we see the whole section's center of gravity is passing through this line. But here, when I observe only the top segment, its center of gravity is here. When I observe only the bottom segment, its center of gravity is somewhere. Okay, from the center of gravities of individual segments to the overall section's center of gravity. That is the answer, and we have got the answer as I2 like this. And I is equal to I1 plus I2, and the summation we have got the overall moment of inertia of the T section about the neutral axis. Now, the next thing, we are going into the distribution chart. So, once we have to do the distribution, we should have to generate step by step, like we have already given for the I section. Here also, for the flange, for the web, one by one. Okay. Firstly, shear stress distribution in the flange. No need of top flange because we are not having any bottom. So, shear stress distribution in the flange is equal to shear stress at the top edge of the flange is 0. Why it is 0? Because at the top edge of the flange, this shear stress is 0. That is the complete extreme edge of the beam. Okay. Next thing, I need to calculate shear stress at the bottom edge of the flange. Okay, in the web, in the flange, at the bottom edge of the flange. Still, I am in flange only, but I am calculating at the bottom edge of the flange. So, that answer is equal to FA y bar by I into B. The main unknown and the main important thing to calculate is A into y bar. So, I am calculating the A into y bar here. So, the A into y bar for the section generally you can see like whenever you want to calculate area moment, first thing FA y bar by I into B. So shear stress at the top edge of the flange. Above that nothing area is there, so F is there, I is there, B is there, but A into y bar. So above that level, whatever is the area, that is nothing. Or below the level also we said yesterday. So for the below level, for the whole area, A into y bar is equal to 0. Or above the level, nothing area is there for the top edge. Now for the bottom edge of the flange, above that level, what is the area that I am shading? So that I can calculate A into y bar. And then I need to use the width of the beam as width of the flange, because still I am there in flange only. And for that A into y bar, what is the area? 100 into 20. That is area. And y bar means distance of centroid of this portion from the neutral axis level. That is 32.22 minus 20 divided by 2. So 32.22 minus 20 divided by 2, that is A into y bar for us. 2000 into 22.22. Okay, so 22.22. In this way we have calculated A into y bar. Now I am going into the things. Firstly, capital F shearing force at the section in the problem they have given. A into y bar. For this level, above the portion's area moment we have calculated, and capital I, moment of inertia of the whole section also we have calculated. And B is width of the beam at the level I am calculating the shear stress. I am calculating shear stress at the bottom edge of the flange. So width of the beam at the flange level. Width of the beam in the flange level. What is the width of the beam? 100 mm. So substituting all these answers, F as 50 kilonewtons. A into y bar we have got as 2000 into 22.22 divided by I, moment of inertia of the whole section. We have got the answer as 314.22 into 10 power 4. And the B means width of the beam at the level I am calculating the shear stress. That answer is 100 mm because still I am there in flange only. Okay, so in this way F A y bar I into B we have calculated and got the answer as 7.7004 Newton per square. That is at the top of the flange, at the bottom edge of the flange. Now I am going into web portion. Okay, shear stress distribution in the web. Now when you see the web, already we have said at the same junction only I'll calculate at this same junction level, but we will calculate in the top of the in the flange level and in the web level. What is the difference? When you see shear stress distribution in the flange, we will use the width of the beam as width of flange. But here I will use width of the beam as width of the web. As it is, the remaining things will not at all differ because the value of area into y bar is the same like the previous. Only the multiplication of 100, 20, 32.22 minus 20 divided by 2. So we have got 2000 into 22.22 as A into y bar. And substituting the remaining values, 50 kilonewtons as 15 newtons, 50,000 newtons, and A into y bar 2000 into 22.22 and moment of inertia 314.22 into 10 power 4, and width of the beam I am using is here the distribution is in the web, so width of the web that is 20 mm, and we have got the answer as it is the remaining previous step. See here A into y bar F as it is moment of inertia, but width of the beam is width of the plane. Now in web as it is F A y bar moment of inertia, width of the beam is width of web. Okay, again even at the junction also, in the top, again in the bottom. So in the web level, in the flange level, these two answers will come. Here I have got the 35.357 Newton per meter square. Now again in the web some other point, that is the neutral axis level. Okay, shear stress at the neutral axis level of the beam. So at the neutral axis, okay, whatever is this at that point I should have to indicate my level, and above that portion is the considerable area for me. Once I said on the top edge of the top flange, again bottom of the flange, so consider the area. Again top of the web, consider the area. Again at the neutral axis of the web, so consider above portion of the neutral axis. Okay, at which level I am calculating, at that level I will use the answer. So this portion is having two types of segments. That's why A into y bar is coming from a part. So that is A1 y1 plus A2 y2. And for the first part, area is 100 into 20. And its centroidal distance only for the first portion. What is the centroidal distance? So here this is my 1 and observe up to here this is my 2 and this is the separation. Okay. So for that portion only we are calculating the stress. First portion and second portion. For these two segments only I am calculating A into Y bar. And the first thing is 100 by 20 into Y bar. Y bar means this measurement. As it is we have already calculated as 32.22 minus 10. Okay, next area. How much area is left here? This portion's area. What is the height? In a total 32.22 minus this height, that is 20. So, and width is 20. So, B 20 into depth 12.22. 20 into 12.22. In this way, I am calculating the measurement and multiplying it with what is the multiplication thing? From the centroid to the distance. So, this is 12.22. So, whatever it will be, half of 12.22. Right? So, 12.22 divided by 2. Once you have enough clarity, you no need to calculate individually. Once after substitution also you can calculate. But the thing is, what is area? What is Y? I am writing. What is the second segment's area? Why A into Y bar is above the level? Because I am calculating the shear stress at that level. The complete above portion is the A into Y bar. First area movement for me. Okay. This value will come under. And then F, shearing force at the section. A into Y bar. Just now we have calculated. I, overall moment of inertia of the section. B, as I am giving the shear stress distribution in the web and at the neutral axis level, what is the width of the beam? That is 20 mm. So substituting all things, F as 50 into 10 cube newtons and A into Y bar from the previous step and I as 314 into 10 power 4.22 into 10 power 4 and width of the beam is 20 mm. So F A Y bar by into B, we will get the shear stress at the level of neutral axis as 45933.284 Newton per mm square. .28 Newton per mm square. Okay. Again, any other point is left? Yes, at the complete bottom edge of the web. As it is the top extreme, it is the bottom extreme. There also the shear stress is equal to 0. Okay. So, I am generating the picture for this. Here I am having a T section and indicated the neutral axis. This is the representation. Now, along the depth, you should have to indicate the points which are like a projection lines. Okay, so this is our representation. And what I should have to do for the shear stress distribution on the right side, how much the value is there, that we should have to indicate. Firstly, from the flange. Okay. So, starting at the extreme top edge, it is 0 and at the bottom of the flange is 7.0714. 0 to some value which is 7.0714. And connecting these two, I have got some value. Okay. So, the measurement here I have observed as 7.0714. And then coming to the web, at the top of the web. At the top edge of the web, we have observed 35.357 Newton per mm square. is the measurement 35.28, and then at this level 35.35. Maybe it's some mistake, we have got that. Okay, so and to the 0, connecting this portion, and here we have got this value and like this, connecting this to the 0. Okay, so 0 to the value, and we have observed at the top, and some maximum value at the neutral axis level, and some value of 0 at the bottom flange. So this is the overall shear stress distribution diagram for the T section. Please don't mind, this one is mistake. 35.28 this value. 35. This measurement is 35.28. Every time you should have to remember this portion, any value is measured from the vertical only. Every value is measured from the vertical level only. Okay, not from this edge. Again, from the vertical straight line we are measuring. Okay, so in this way we will calculate or generate the shear stress distribution diagram, as I have already indicated at the bottom edge of the web it is 0. So connecting all these things, we have generated the shear stress distribution diagram for the T section. Okay, in the next class we will go into the shear stress distribution for the triangular section.